Hello, here's Malban again, and I would like to talk about Vide again. Vide Vectrex Integrated Development Environment. This time I would like to show you something about the debugger integrated in Vide. The debugger in general can be used to do two things. Debug your own programs and find mistakes, errors, or some other unusual stuff. And you can use B, the debugger, to disassemble and comment foreign programs that you would like to get to know a little bit more. I will concentrate today on debugging. So for this purpose I start Vide, the editor, with a little demo program I've written the last few days or hours, and I would like to show you the debugger using that. As you've seen before, you can start your own programs with a start button or the debug button. This time I would like to start with the debug button. Then the disassembler window, the debugger window, will open right from the start, and the first breakpoint will be set to the first actual instruction of your Vectrex program. So the breakpoint will be hit, and it's just happened. Here you see the little debug message in Vexi, and the current location that the program is at is marked bright blue. You can also see when a breakpoint is hit that the register window opens automatically. Here you can see all instructions of your CPU. While we are at it, there are a few buttons I would like to mention. First, this little camera button over here. If it's switched on, there's a green thingy at the bottom. If this is enabled, then the window is updated as soon as it is possible. In debugging mode it is updated, or all windows are updated always anyways, but if this is switched on, then while running a Vectrex program, all registers are updated all the way, all the time. So what you see here is the actual debugger screen, dissi. If you debug your own program, you will most likely feel quite at home, because it looks very much like your own editor. Just in comparison, here you see your edited program, and you can see, once we scroll to a location where you can actually see something, here is a start label. Here you find the start label, or more than one. Here you see the actual instruction codes, LDA, STA. Here you see the same. And here you see the actual variables or constants that you defined, which you will also be able to see here. All this information is generated automatically from your own source code, and the assembler passes it along to the debugger. Actual so-called control file is built, and the control file is read by dissi. You can build your own control files, but that at another time. So what you see here is mainly a window with a table in it. The table has many columns. The columns that are configured right now are the address, the actual address of the instruction. If an instruction has a label, or labels are displayed here. The contents, the actual memory contents in hexadecimal bytes. The mnemonic, the assembler instruction or pseudonymonic of the assembler. The operands, usually numbers or variables, as you can see here. The cycles, how many cycles the instruction takes. If the instruction refers to another address, that can be a jump or a relative jump or whatever, then the address is shown over here. Your comments of your actual source codes are also displayed here. The only drawback is that you have got only one line here. If you have multi-column, multi-row lines, then these lines can be displayed using the tooltip. Also displayed is a direct page register if it is known. If it is not known, then a question mark is put over here. So then the other buttons over here. Here you can see a single step. We might do that right now. Single step into your program. You see the changed registers are always marked red. The unchanged registers remain black. Many windows have tooltips, as you can see here. If I put the mouse over the register A, you can see that it's what its decimal number and its binary number is, and the hexadecimal number is always displayed. Same goes for the other registers. You can interact with the register window. If you double click any of the 16-bit registers, the debugger will jump to that location. If I do that now to the, I scroll to some other location and I double click the PC, then you see the window jumps back to the PC register. The others work as well. So you can further single step into your program. At one stage, sooner or later, you will probably find a subroutine. Well, let's find them here. Here you've got a subroutine, direct page register to C8. There's something wrong over here. With that, you can jump into the, or you can go into the subroutine if you use a single step, or if you hit a subroutine, you can overstep the subroutine. This is with the overstep instruction. Then the complete subroutine is executed and exited, and the next breakpoint will be set after that same instruction. Attention a little bit, this is mainly useful for subroutines, but can also be used for any other instruction. But beware, branches, conditional branches might not be met, and if they are not met, the instruction, the breakpoint which is located as the next instruction might not be reached. So if you overstep a conditional branch, you might actually not overstep it but run the complete program, since the condition might not have been met. Just to keep that in mind. If you are in a subroutine and it is quite boring in the subroutine and you don't know how to get out because there's a timer counting down for eternity or something like that, you can use a step out. This means a breakpoint is set at the topmost stack location, and you step out of the actual instruction. You can do that now, and you see we return after the wait recall that we were just executing. You can see the current stack over here in the register window, but beware, this is only a stack for calling of subroutines. This is not the actual stack with all the bytes and bits you might have pushed onto it, but it's only a collection of subroutines that you stepped into. So you can step out again. You can run the program, continue the program just hitting this little bug over here, and you can break the program hitting the bug again, break and unbreak and break and unbreak, and so on. What else is there? There are quite a few helpers available, as you might have seen before. You can, as in Vide, double click on any mnemonic and you get the help. You can double click on known variables or known subroutines, then help is also displayed. You can this is a trick you probably don't need with your own programs, but it's interesting nonetheless. This via control, via registers, these are direct page addresses. As you can see here, the instruction is only 16 bits and the actual address is only an 8-bit address, but it gets resolved into a via control register, which is located at DOOC, not only OC as you see here. Dissi can do that because it knows, as you can see here, that the direct page register for this address is supposed to be D0. So if you actually change that, we can do that by setting it to another direct page location. Then dissi does not know any longer that this is actually a known direct page register, and it changes it to the actual hex value. The program will probably still run okay, since the actual content did not change, but it's not as readable anymore. So change it back. Yeah, you could know that. What else can you do? You can inspect all your code that you are doing. Well, let's run a little bit. Let's see a location that might be interesting. This is more or less interesting. I can show you. As you can see, I haven't shown you before. You can open a pop-up window and you cast each row of your disassembly to a certain type. You can cast to code, to byte, to word, to character, or to binary. I can do that. If I cast this to code, then it will be a layers whatever, which does not make any sense. But we know it's a bytecode here because this is a bitmap data of that little bitmap over here. I know that because I programmed it. And we can actually debug the bitmap over here if you use this button over here. This shows the memory dump. This is an actual memory dump window. And if we click active here and raster there, then we can mark the locations over here, and the actual raster data that is selected over here is displayed here. So I know that the width of my raster image is, I think, 3. You can change the width over here. It seems to be 4, not 3. And you can change the size of it here. And I use too many locations. I go back over here. Now we've got exactly the image in our dump window over here, which is also selected, as we can see. So you can inspect your code as well as your images and your vector lists. Let's look for a vector list of some sort. Animation list. I think this is an animation list of the actual cube over here. We mark one cube entry here. This is now interpreted as raster data, which it is not. We must interpret it as vector data, and it must be the correct vector data. I know perchance that is a draw vector list mode. When you know that, or if you experiment, you can change your vector list types over here, and at some stage there might be something useful seen, which is at exactly that location. You can inspect your actual memory locations for vector lists, and you can also see the selection over here again. You can change the size of your output over here. You can switch to non-active, then it doesn't change anymore, at least not the list over here. Well, why was it active again? Don't know. Not active. Okay. That's that. Then let's run it again and let's press a button. Go over here. Here you see a little man running. Now we want to know when this scroll text really is drawn. This is a bad example. This is debugging now. We can inspect our audio registers. We might do that over here. These are all over our PSG registers. which do not change, as you can see, but if I switch on the changing, you'll see that it gets updated all the time. You can actually record YM records over here, either by address or by cycles, as data, as bin, or as YM files. I won't do that right now, but you can inspect all your registers over here. You can look at the speed of your actual program. If you open a tracking window, again, you should switch it on. Now you see that this screen is updated with at most nearly 30,000 cycles, so it's still quite a fast demo at this. You can show all your VIA registers. There are two displays over here. This one, this big one, are all the VIA registers. VIA register null or B. You've got many tooltips which describe which kind of settings each register may have or may not have, or what's the meaning of them. The different colored registers over here means green is output, blue is input, because register A and B can be set each bit individually to input and output. In opposition to the VI registers, you can switch them on also, but it gets really slow over then sometimes. There are the analog data that you can see. In opposition to the VIA values, the analog values are values that, well, how can I describe it? Well, the actual analog parts of the Vectrex represented in the emulator. There are a few cycles difference usually between the VIA actual registers and the analog parts. This is what makes emulation quite exact, I think. Also in the analog window you can see the buttons and the joystick values, which can be updated over here. I can move the joystick and then you will see that in joystick 1 the value changes, and I could press some buttons and you see that the button value also changes. Then we've got the variables window. This window shows the RAM locations. You can also switch that on and you see that it gets updated all the time. This does not show all RAM location, but only RAM locations which the debugger thinks are used at the moment. If you think you need another location which is not shown right now, you can add it with this plus button. As you can see, the shadow registers of PSG are not all displayed. We can, for example, add $C801, then the shadow register will also be added for that, and so on. Usually that is not needed very often, but you can use it. So what else is there? You can set breakpoints to these actual variables. You can add a breakpoint if the variable is read, if it's written to, or if it reaches a certain value. So breakpoints can be set on variables also. Another feature is show labels. Labels, it does not seem to be very interesting right at the moment, but you can use that as an actual browsing utility of your code. So if you want to jump very fast to, you can sort it and sort the list, and let's sort it. And you want to go to your animation, I don't know, vector 0, 0, you can jump right to these locations from your actual labels listing over here. So if you want to know where start main is, Then we jump to start main 2. This is a second window over here, and we are right at it. We don't have to scroll through the whole code, just have to know what it's called. Then I already showed you the PSG registers, breakpoints. This is the breakpoint window. All breakpoints that are possible are listed, that are currently active, are listed here. If you do not want this breakpoint anymore, you can actually delete it over here. To very fast set a breakpoint to just a memory location, you can go to any line and press this little button over here, set breakpoint. We are now at main 2, so this breakpoint is not reached, but if we go back, then now we reach our breakpoint, PC location 3C, and you can see that this breakpoint actually was hit and we removed it. You can set and remove breakpoints also with a space bar. Okay, that's that. With this button over here, you can actually export your current dissi content to a file, and this file will be compilable or assemblable with ASCII. This is not very useful for your own programs, but if you want to debug other people's programs, this might be useful. The next button also, this is save all gathered information to a CNT file. This is also not useful for your own files, but if you debug other files, then all your comments, all your labels, and everything you did within dissi will be saved, and you can reuse it later on. Vector screenshot, this is also not very useful for you right now in your own programs, because this actually does a screenshot of the current vector list and saves it as a vector list that you can edit in Vecchi. The last button that I did not explain yet is the second last, is this with the little mouse. If you enable this button, select vectors and show information, then a little cross is displayed within Vecchi, and you can select a vector, click on it, and another window is open, and the vector is more or less explained. Explained means this the starting point, the end point within Vectrex coordinates, the intensity, and the count of vectors currently displayed. We must step once, I think, before we can actually see that. This has nothing to do with actually this vector we just selected, but this is a count of all vectors together. And below here you can see the current mouse pointer location in Vectrex coordinates. So again, if we select the vector over here, you can see that the starting point is at 609, and if I move the mouse button very slightly, I think we should. So now 609, it's still hard, and excellent. 1000 location. Anyway, you can see the mouse pointer gets updated, and these are the actual Vectrex integrator locations. So you can find your locations a little bit easier. You can also see from the vector, from that window over here, the actual vector was displayed using after this instruction. Switch the light off. We are in a draw sync list rm, and at this location the actual vector was finished to be drawn. You can see that clear 0A. This is actual shift register. We do not have the direct page register set here, so we can actually use what I showed you before and cast it to the direct page register, and you see that the clear shift reg finished this vector, and the vector finished drawing was displayed. This is actual program counter location where this vector was finally displayed, and this is the stack of the subroutine calls. So you can see this vector is actually displayed using the draw synced list within the main program. This is probably also more useful if you debug foreign code, but nonetheless quite interesting, I think. This button over here, probably also not all that interesting for your own debuggings, but I'll explain it anyway. You can reset dissi and start disassembling again. You might ask what that is useful for. I can show you. If you have foreign programs, then you've got the option somewhere over here. For debugging, you can switch on a code scan in Vectrex. If in Vectrex the code scan is active, information about the program is collected internally. For example, what the direct page register is, if data was actually, or if code was actually executed at a location, or if a location was only read, then it's probably only data, and so on. So the disassembly of a foreign code is a little bit easier if you actually do a code inspection before, and you do a reset after that, and then all the information collected are integrated into current disassembly. If you entered data before, you should always save your data to the control file using this button. This button is very important if you debug foreign programs. So what else have you got? We've got this area down here, which I have not really explained yet. Here you can execute command line stuff. Pressing H or help will list commands that you actually have. I will not explain them all. I'll just talk a little bit about it. You can do a hard reset, a soft reset. You can do a go, which is actually the same as the bug button. You can, but also go from a specific location. If you use this button, it just starts where it just left, and here you can start at go 1000. Then the program would start running at 1000, which is probably not a good idea right now. Cycles, if you press just C, you can see this many cycles where the emulation already runs. If you do a C0, then the cycle count is reset to 0. If you do C again, then you can see how many cycles have passed since the last zeroing. While running, this might not be very interesting, but if you want to know how many cycles the subroutine used, then you can just reset the cycles before, run the subroutine, and print the cycles thereafter, and you know exactly how much cycles it took. But you can also say run cycles, then the program will only be run for at least so many cycles. And you can do a count cycles between two addresses. This is quite similar to Tracky. You can enter breakpoints to certain locations which you cannot enter otherwise at the moment. So you can, for example, set a breakpoint if a bank switch occurred, or you can set a breakpoint if via ORB bits 0 to 7 change in any way, or similar things. You can clear all breakpoints. You can do a label reset. Information about the current cartridge which is run. This shows the name, how many banks are used, the checksum, and whatever hardware might be required to run the cartridge. You can remove automatically generated comments, which does not occur for your own programs. You can switch bank switch info on and off. If you do bank switching, then dissi outputs a small message, bank switch occurred. You can poke to a location. This you can poke to any location. Let's, for example, say we want to change the name of our own program, and we poke to 1141. So it's not raster example anymore, but aster example. So we can see we change the memory location. This works for all locations, be it RAM, ROM, or input, output, or whatever. This pokes everything. You can open a CART window. This is a window which gives information about hardware of cartridges, which does not mean anything for this demo right now. You can open a JOY window, which gives information about all joystick devices. You can also switch update on off over here. And attention, you must also know which port you want to use, because for example, if you want to watch Imager, default for this window is always 0, but if you want to look at the Imager, you have to switch it to port 1, otherwise you won't see any information here. But we are not using any Imager right now, so it doesn't really mean anything. The last thing you can do over here is set register value to something. So if you want to change, let's stop it. Now we have register A set to 20. If you want to set register A to 40, you can do it this way. This also works for all registers. Might be interesting for some debuggings. I'm sure I have not explained everything yet, but we can do these little things over here again. This is a search. The search goes for labels and for I don't know. We search for main, then we find it in the comments. Then we do not find it in. Yeah, we also find it. This is the two locations which the search is good for. It looks for labels and it looks for comments. This is the things you can search with search. The other thing you can use down here is highlight operands. So if, for example, you want to you want to find every location that has something to do with music, then you can enter music over here, and each operand which uses music in any way is highlighted. This is also quite useful sometimes. Another thing, if you click on a label, the label you clicked on is also highlighted in a different color, or in this case you can see it's part of the label is highlighted. Actually everything there where main is involved. Usually, I don't know. Do we have anything here? What I didn't show yet is extensively how you can change the looks of your data. Let's look for the C1 data again. Here you can see this is the actually Chris. We've seen it before. At the moment these are direct bytes. We can tail these memory locations to group into groups of, I think 4 it was, wasn't it? And if we now also tail these bytes, that they are not really bytes but binary data, we can do that also. Cast to binary and expand it a little bit. Then you can see, if you go back a little bit further, that this is the actual bitmap. So you can cast memories to different kinds of display options. You can join bytes to a certain number. You can join all bytes or you can unjoin bytes. You can set the direct page register, and you can set label to data. I will explain that at another time because it's also not very important for your own programs. Well, I think that were many things. One last thing I would like to show you. These 4 buttons that I did not explain. These are, and then I will finish for now. As we have seen before, we can jump to locations using the addresses. The locations you jump to are remembered, and you can go back to the locations that you've come from. You can browse forth and back to the locations that you jumped to within dissi. This is sometimes very helpful. Also, you can, if you're in debug mode and you enabled it, let's run a little bit. Now we stopped here. If you want to know how we came to this location and how the registers changed before, you can step backwards. These are these 2 buttons. Take last instruction back, or again execute the last instruction. So we can actually go back in time with these instructions up to what is defined in your configuration, which is 2000 rollback buffer, which you cannot change it yet. So for 2000 instructions you can actually go back in history and see what did occur before. Every window that is changed or influenced in any way will be updated according to these changes, as you might or might not see right now. Well, you can't see very much, but anyway. Actually, the button over here does exactly the same as execute again, whereas this one does actually execute and this one steps 1 forward in the buffer. If you once do a single step forward, you cannot step forward again. I mean, if you really execute a step, you cannot step forward in your buffer again. You can only do that while in the buffer and not execute another step. Well, I think that was enough debugging for today. I hope that was interesting. And I say bye bye and thanks.